Hello there. Let's do link aggregation, because redundancy and improved performance is awesome. Now let's tackle that redundancy first. To do the redundancy, we're going to have multiple links between the same two appliances when it comes to link aggregation. 2 links, 2 devices. So here we have 2 switches with 2 cables going between them. This is not unusual. We saw this before with the spanning tree protocol video, and it gives us fault tolerance. But usually, spanning tree protocol would cause one of these links to be inactive. The reason being, it can cause a loop. So if we have spanning tree protocol running on the switch network, this is probably what ended up happening. We would have one of these ports going into an alternative or blocking state. Now, in terms of the redundancy, if one of the links fails, the other one can carry on working. However, that will cause the entire spanning tree protocol topology to reconverge. So if there were other switches connected here, they would have to go through the whole relearning process that we saw in the STP video. And the other problem with this type of redundancy is that the link's capacity is going to waste. The interface and link that is in the alternative or blocking state is not being used. So I've got 2 connections, but only one of them's actually getting used. And this is where link aggregation comes to help us. So let's check out the basics first. We are going to be taking multiple interfaces between the same 2 devices and making them work together as a single logical interface. This is kind of like what twisted pair cables are. If you think about a twisted pair cable, we've got multiple wires inside of one cable, but we still treat it as one connection. So would it be that weird to have 2 twisted pair cables that we treat as a single logical connection? Not really, because if we have 8 wires in one cable, what's wrong with 2 cables being treated as one interface or connection? And that is literally how the devices see it. Multiple physical interfaces working together and being seen as one logical interface. Now, the current standard that defines link aggregation is the IEEE 802.1ax 2008 amendment. Please note it's 802.1ax. Don't confuse that with 802.11ax, which is the Wi-Fi 6 standard. Now, to make matters more annoying and confusing, there are quite a few names for link aggregation. Some vendors and courses will call it an eth-channel. Others might call it an eth-trunk. Some call it Ethernet bonding. And there are loads more names. Believe me, when I went to go and double check what variations of the names exist, I forgot how long that list actually is, and I'm pretty sure it grew since the last time I looked at it. So anything that refers to multiple interfaces working together, or sounds like us making 2 interfaces into one, like bonding, would probably be link aggregation. Now, link aggregation has a protocol called LACP that's there to coordinate the interfaces working together. LACP will be operating between the 2 appliances, and it's going to use LACP DUs, Link Aggregation Control Protocol Data Units, to communicate information between these 2 devices so that the aggregated links can work together correctly and consistently. Now, one appliance will assume a role called the actor. Let's say it's the one at the top. That's going to be the actor. Now, the actor is going to dictate which interfaces are going to be active and what they're going to be doing, and which ones are going to carry which packets or sessions, or however the link aggregation is going to manage the workload. So out goes the messaging. The other appliance is going to be referred to as the partner, the one at the bottom. And the partner simply follows the actor's instructions around what must be done and how it must be done. The roles are dictated by a priority number that is very similar in mechanism to spanning tree protocols. Lower the priority number, more likely that switch will become the actor. Now, one thing to bear in mind when it comes to this actor-partner role, this is going to be per aggregated link. So even though that switch at the top there is the actor, if it had a connection to another switch, besides the one at the bottom there, that other switch might have a better priority, and in that relationship, it might be the partner. So this is a per link role, not a whole topology role as with span tree protocol and the root bridge or switch. Now, link aggregation details that we need to understand and be comfortable with, otherwise we can very quickly lose track of what's going on. You're going to hear about the LAG, or the link aggregation group. This is just the name we give to the interfaces working together. One thing to be very, very mindful of is we are limited to having a maximum of 8 interfaces in a link aggregation group. So between these two switches, I could not have anything more than those 8 connections. But realistically speaking, 8 connections between the same two appliances is quite a lot. If we look at your average enterprise switch, often it starts around about 16 or 24 ports. That is between half and a third of the interfaces between the same two switches. And some of you might be saying, yes, but wouldn't more interfaces working together be great for shared workload and redundancy? And yes, I'd agree with you. But if something were to take out 8 interfaces, I don't think having an additional interface or 2 would make much difference. The reason why we do have as many as 8 interfaces in a link aggregation group is so that we can have a mixture of active and backup interfaces. Now, the idea of active and backup interfaces is that some of the interfaces are going to be working and carrying data, and then you can set some of the interfaces to be backup. In other words, they're not going to work until one of the actives fails. The benefit of doing this is we will get better bandwidth with link aggregation than we would with just relying on span tree protocol and 2 or more redundant connections. But we might not want to lose performance when a failure does occur. So of those 8 interfaces, I might have, let's say, 6 of them active and 2 of them in a backup role. So that if one of the active ones fails, one of the backup ones kicks in and takes up the workload, and the users won't see a change in the network's performance at all, which will buy us some time to fix the issue. Now, as I've been mentioning, link aggregation does affect speed. We are going to be having these interfaces working together. Now, there are 2 main modes of operation. The first one is referred to as normal or manual mode. And what happens here is the interface speeds and duplexes will have to match so that they can be added together. So if these 2 interfaces are both 1 gigabit per second and we're running this link aggregation group in its normal or manual mode, whichever term the vendor prefers using, we would see an overall bandwidth of this aggregated interface at about 2 gigabits per second, which is pretty cool. I'm now going to have 2 gigabits per second worth of throughput here instead of just 1. Now, we have to be careful though, because if we are running in normal or manual mode and the speeds do not match, the slower interface, or if it's more than 2, the slowest interface will pull the rest down. This is an auto negotiation factor. So if one of these interfaces were to be running at 100 megabits per second, it will pull the faster interface down to 100 megabits per second. Auto negotiation causes these interfaces to work at a speed that is compatible for everybody, and you can't work faster than the slowest interface. Now this means that instead of getting 1.1 gigabits per second, we'll be seeing a total of 200 megabits per second. And if our goal between these 2 switches was to have redundancy and increased bandwidth, well, we failed at the increased bandwidth, because now instead of getting 1 gigabit per second, we're getting 200 megabits per second, which is kind of disappointing. So if we want to do better than this, or have a variety of interfaces, there's a setting called mixed mode, or LACP mode, where if the interface speeds don't match, we will still add the interface speeds together, and LACP will institute a load balancing method that will adjust and favor the faster interface for the majority of packets. This will allow us to have an interface at 100 megabits per second, and it will not pull down the 1 gigabit per second interface, meaning this aggregated link would work at 1.1 gigabits per second, which is pretty cool. However, with LACP mode or mixed mode, if both interfaces were a gigabit per second, we would still get 2 gigabits per second, which has led to that setting being a very, very popular option for network administrators, because then they don't have to worry too badly about mixing speeds and interfaces together. I do still encourage, though, that you should try and keep the interfaces in an aggregated link around the same speed, just for the simpler overall improvement and the presumption of, okay, add all the speeds together, and that's the effective throughput. Now, how does STP and link aggregation get along? It's a very good question. Well, let's say that's the root switch. Spanning tree protocol will not see the physical interfaces that make up an aggregated link. Just like under normal circumstances, spanning tree protocol does not see the individual wires that make up a twisted pair Ethernet cable. So STP will work on the logical interfaces on each end of the connection, or basically on each switch. So STP would see a single logical interface, and on the root switch it would become a very big, very fast designated port, and on that other switch it would become a very big and fast root port. And even if one of the physical interfaces goes down, spanning tree protocol probably would not converge around that failure, because it still sees the aggregated interface as up and working, albeit a bit slower than it was before. And the only thing that would cause these ports to change roles and the STP topology to reconverge and all that stuff would be if there was a lower cost or faster pathway to that root switch elsewhere in the network. So basically, if there's a failure with link aggregation, it doesn't necessarily mean spanning tree protocol has to reconverge. It can carry on working as it was, just a bit slower. And in my opinion, this is a fantastic way of achieving redundancy, because obviously if everything goes wrong, STP finds a way around the failure if there is a way. But if it's a minor issue, we don't have STP interrupting network communications while it sorts itself out. The most the users are going to experience is a bit of a slowdown in the network's overall performance. Now, in terms of where will we see this in use? Well, pretty much any LAN where you would like some redundancy and improved performance. But we can run link aggregation in all of its variations and forms between two switches, as we have been talking about up until this point. But we could also do it between two routers with Ethernet interfaces. I could run it between a router and a switch. I can even run it between two firewalls. Now, the reason why we would do this between two firewalls is there are design practices where we would have two firewalls acting as redundant filtering appliances going into or out of a network. And to make sure that they are working effectively, we would want them to be able to see each other and their status. We call that connection between the two a heartbeat connection. So if one of the firewalls goes down, the other one knows it's gone down and it can kick in and take over the workload. But if I have only one cable between those two firewalls and that cable fails for whatever reason, both firewalls will think the other one's down. Whereas if I use link aggregation, I'm less likely to have a single cable fault causing both firewalls to think the neighbor is down and both trying to take on the other one's workload, causing possible confusion and issues with forwarding. So this would be pretty useful between two firewalls for the heartbeat messaging. And then, most obviously, we'd probably want to do this between a switch and a server, as servers are super useful and definitely an end device worth having multiple connections to. Because if one server can't communicate in the network, that can affect many, many people. I probably wouldn't do this on a desktop computer for one user, but yeah, definitely a server. Many people would benefit from this. The only thing is, it might be referred to by different terms on the server side. Server administrators often will refer to this as eth-teaming, eth-bonding, eth-channeling, and even more. So just be prepared whenever you, as a network professional, are dealing with a system administrator of a server, that they might be using a different term to describe making two network interfaces work together as one. But that is all I need to cover with the basics of link aggregation for you all. Just be aware it can go by a variety of names, channel bonding, link aggregation, Eth-Trunking, there's a whole bunch of them. But as I said earlier, anything that implies two or more interfaces working together is going to fall under the category of link aggregation. I'd like to say thank you for watching this. I appreciate it. And if you have any friends, family members, peers, colleagues, etc., who are interested in learning Network Plus, don't be afraid to share this video with them. Otherwise, I will catch you in the next video.